Step number 9 is the Laplace equation for pressure. Step number 10 is the Poisson equation for pressure. And we do these steps one by one so that you have a very nice chunk of work in your programming that you can actually test your results and be sure that you're correct before you move on to the next. You see? That is the purpose of these little chunks, incremental steps that we are giving you as assignment. Because when you do Laplace equation correctly, you already have all this bit of code, and you see your next step will reuse most of that code. The only difference is going to be that your right-hand side is no longer 0. It's going to be equal to something. And then we're going to put that into the Navier-Stokes equation. You've already done 2D Burger's equation, and all we need to do is add this part, and you're all good. You see where this is going? All right. So now we do the Laplace equation. You see, here's our Laplace equation, and we're going to discretize the Laplace equation with a second order centered difference. So we write P. There is no time here, but we're still going to write n as a possible time, but n is going to be across the board for all of the p's that we write here. But in space, we are using a center difference for this second order derivative. So we have in x, I plus 1 I and I minus 1. Divided by delta x squared. And in y, we have j plus 1 j and j minus 1 divided by delta y squared. And all of that is equal to 0. Good. So now this is an explicit scheme for, we're going to isolate the center point here in the following way. Let me write it, let me write it and then explain it in a moment. We're going to isolate the center point, P, N, I, J, and it's going to be, so I'm going to multiply this by delta y squared and multiply this by delta x squared, and then these terms, I isolate them on the other side, and then I'm going to divide over by 2 delta x squared, delta y squared. Okay, so you can see that at the bottom I'm going to have 2 from these terms, delta x squared plus delta y squared, and I have delta y squared times, I only have I plus 1, comma j, and I minus 1, and I also have I j plus 1, I j minus 1. So I've written here the discretized form that we're going to use for step 9. I'm still going to explain some more things about it, but just look at it for the time being and be satisfied that at least our algebra is correct. That is, you're satisfied with that? You're satisfied with the discretization and with our algebra so far? Okay. So now let me write what the assignment is going to be. You're going to start with an initial condition. Let's call it initial condition P equal to 0 everywhere. You're going to calculate in a domain between 0 and 2 in the x direction and 0 and 1 in the y direction. This is a little sloppy, so let me write it again. And we're going to have as boundary conditions P equal to 0 at x equal to 0, p equal to y at x equal 2, and we're going to have a Neumann boundary condition dp dy equal to 0 at y equal to 0 and 1. Let me say that this problem has an analytical solution that you can obtain by separation of variables, the method of separation of variables in partial differential equations. And the analytical solution looks like this: p x comma y equals x over 4 minus 4 times an infinite sum, n equals to 1 with n odd, of these transcendentals that I'm going to write out. We have n pi squared here, and the sine, hyperbolic sine of 2 pi n, 1 over that. And we have hyperbolic sine of n pi x, and finally the cosine of n pi x. So this is the analytical solution to this problem, and I give you the analytical solution in case you want to compare with your computer results. And this is all the all that you need for step number 9. But let me explain a couple of things before I leave you with that. First, note that as the Laplace equation is typical for diffusion, or the Laplace differential operator, so that would be more appropriate, I guess, is typical of diffusion. And diffusion is a isotropic phenomenon, then it has to be discretized with a central difference. In order for the discretization to be consistent with the physics. We've discussed this before. In no way can the numerical approach be inconsistent with the physics that it represents. And we saw what the consequences of overlooking this was, for example, in the convection equation. You know, the convection required us to use asymmetric difference schemes that were biased towards the direction of flow or the direction of the velocity. So in this case, the diffusion phenomenon is isotropic, and so we have to use central differences for the discretization to be consistent. With the physics. That's our first commentary. And in fact, this second order finite difference, this second order central difference in both directions, x and y, is the most widely applied difference operator for the Laplace. The most widely used numerical scheme for the Laplace operator. It is also known as the 5-point difference operator, And as you can see in this figure that I've drawn of the stencil of the numerical scheme, it's obvious why we call it the 5-point difference operator. But note that what we're going to do really is use these 5 points to obtain this point, which is right there in the middle. Okay? Let me explain this. What happens is this numerical scheme, this is an actual iterative scheme. An iterative method for the steady state. Remember, the time derivatives don't appear. So it's a steady state pressure. And this iterative method is equivalent to a time variable. It's an artificial time. Okay? Artificial time variable. So, suppose that in our previous scheme, take, for simplicity, let delta x equal delta y, so that we have to write less. Then the discretized scheme that we just wrote in the previous slide was p I plus 1 comma j, our center difference, minus 2 pij plus pi minus 1j, and the other terms were pij plus 1 ij and pij minus 1, I've run out of space, equal to 0. So this basically is a linear system of equations for all the points in the grid with a coefficient matrix which is pentadiagonal. So really the initial condition in this case that I've given you, p equal to 0, is like an initial guess for an iterative method to solve this linear system. You start with p equal to 0, and like I've said here, you use all these 5 points there. They're all going to be 0 in your first iteration, but when you calculate them and you get a first value of this point here in the middle, you span and sweep all of the points of the mesh, and you update your value of pressure. You do this again, over and over again, and this is a iterative method which is actually equivalent to the Point-Jacobi iteration. For solving linear systems. And so I want to give you some tips for the assignment for this step. So choose a number of steps, iteration steps. It's equivalent to a time step, but it's an artificial time, which you can increase over time as you gain confidence with your code. Don't put 1,000 in the first go. Start with 100, but then you can try 1,000 if you want. But perhaps visualize every iteration on every other iteration, or every 5 or something, and visualize the iterations as they move on, so you can see the solution. You will see the solution basically relaxing to the steady state. So when you do that, visualize each step of the iteration. Think about what the boundary conditions are doing. Okay, you're going to impose boundary conditions on this, and think about what the boundary conditions while you're looking at this, the plots of this thing iterating. And also think about what the PDE is doing. Think about it. Imagine what what's going on here. As you look at the visualization, this is a very powerful tool to visualize a numerical solution and understand then what the equation is actually doing. Basically, he will see as the solution tries to conform to the boundary conditions in the smoothest way possible. You will see that happening. Okay? That's step number 9. And maybe I have some, yes, pseudocode. It's very short. You can see now that you understand there was a lot of things to explain about this, but if you turn into a code, it's not very much. This is a MATLAB style. It's not really pseudocode. It's a little bit of a MATLAB syntax here for you to understand without any of the plotting. You can see here that we have defined x and y to be our list of points in the x and y direction. This is a 2D domain. And I've filled up the matrix of values p with zeros. That's just my simple initial condition or initial guess. And I'm going to work in MATLAB, and you can do the same in Python, with the arrays, the two-dimensional arrays for x and y. And I fill the values of p for the next iteration with our difference formula, like we've just written it out. And the number of iterations, I put 1,000 here. You can try with 100 at first, so that until you've got a code without bugs. And here are kind of a very simple way to impose the boundary conditions. And you can see this, of course, pseudocode again if you want to on the record of the recording of the lecture. So you shouldn't have any trouble with this. You already know how to use your array operations in Python, so you shouldn't have any trouble. Perhaps there will be some challenges on producing a decent visualization of the solution. As you have learned already, just programming a solution is just half the work. Producing proper visualizations of the solution is quite another challenge still. So you need to work with that. All right? So, step number 10, the Poisson equation. So now we have the same thing as before, with the only difference that we have a right-hand side. So, we discretize, we'll write this again so we all get really used to it and you can write it in your sleep. Discretize the Laplacian operator with a second-order center difference approximation, Pn I plus 1, I minus 1, Pi j plus 1, ij minus 1. Equal to, now we're going to have b and ij. It's also discrete. So unlike the Laplace equation, we have a source term. That's the only difference. And we can transpose, as before, by, in this case, we really want to write a iterative method, so Pij we have Pi plus 1 comma j plus Pi minus 1 comma j times delta y squared ij plus 1 plus P and ij minus 1 and delta x squared and minus b I j delta x squared delta y squared and everything divided by 2 delta x squared plus delta I of y squared. Here we are. So now Our initial condition for this part of the assignment, p equal to 0, as before, everywhere. In the domain is going to be between 0 and 2, and 0 and 1 in the y-coordinate. Boundary conditions, p equal to 0 at x equals 0 and 2, and y equals 0 and 1. And we have a source term now, which is going to be 2 spikes, bij equal to 100 at this point of the mesh where I is equal to the number of points in x divided by 4, and the j index is the number of points in y divided by 4. bij is going to be minus 100 at this other point here, 3/4 in x, j equals 3/4 in y. So these are just 2 spikes, and bij is going to be equal to 0 everywhere else. And so again, you want to look at plotting consecutive iterations of the solution and looking at it and thinking about what the PDE is doing. Try to think about that. Try to make some sort of physical interpretation of what the PDE is doing. And that will teach you something about the different terms that appear in the Navier-Stokes equations and what they do in flows as well. So now we're almost ready, actually, to do the Navier-Stokes equations. Now, for the pressure Poisson equation in discretized form, we're actually not going to use the correction term that is multiplied by the viscosity. If you recall, there was a term that was kind of a convective term, there was an unsteady term, and a term that was multiplied by the viscosity. That term is actually very small, and you can actually get good results ignoring that. So you can do that if you want, or you can code the whole thing with the whole term if you want. So I'm going to write it without that. Before we go to step number 11, we have the pseudocode right here, and you can see that the only difference is we have these 2 spikes at particular points, and here on the right hand side we have the same as before, but we have in addition just this guy over here. It's the only difference with the previous code. So you can see how you're going to reuse most of your code for this part of the assignment. Nothing here too mysterious, I hope. So for Navier-Stokes equations, well, Navier-Stokes, let's write it all out again. We're going to discretize the momentum equation in 2D. So we have 2 equations, and you've done something similar before. You've done your 2D Burgers equation. So this has only one additional term, this pressure here. So you will be able to reuse and edit a good part of that code. This is a V. The pressure, dP dy, plus viscous term with the Laplacian of V. Okay, so I'm only going to write these terms for the Poisson equation of pressure. So we have this term over here, which is rho times du dx plus du dy dv dx plus dv dy, and we have the term rho d dt du dx. This is let me just write this and finish. Like I said, I found a couple of mistakes this morning, so I'm not 100% sure of everything here. I'm going to have to double check again that I've got everything correctly, but you can help me out if you find some mistakes and you post it on the discussion board. We can sort them out. The discretized form, I'm not going to write everything. I'm just going to write the first equation for you so that you can see that this is all possible to do. The time derivative is, of course, un plus 1 at point ij minus un at point ij divided by delta t. And then we have, and this you've done already for the Burger's equation, uij times, this is a convective term, so we use a backward difference in space to be consistent with the physics that it represents. So uij minus ui minus 1 j divided by delta x, and the second term is with v here, vij, and again it's a backward difference in j now, ij minus uni j minus 1 divided by delta y. So we got here all the terms of the left hand side, and we need to have minus 1 over rho, the pressure term. For the pressure term, we're going to use a center difference, P n I plus 1, comma j, minus P I minus 1, comma j. So this is taking 1 point from each side of ij, so we divide by 2 delta x, plus our viscous term. And so for our viscous term, we use the usual discretization for the Laplacian, which we've done before. We've just done it for the pressure as well. I plus 1, comma j, I, comma j, and I minus 1, comma j, divided delta x squared, plus I j plus 1 minus 2 I j plus un I, comma j minus 1, and divided by delta y squared. For v, it's exactly the same thing, and so I'm not going to write it out because already my hand is achy. You can basically replace v there almost everywhere, and also you would have to put, of course, the derivative of p with respect to y in that second equation, and apart from that, it's very clear what you need to do. So now we want to do the Poisson equation. So we're almost there. Pni plus 1, comma j minus 2pi, comma j plus pi minus 1, comma j. So that's our second order center difference for the second order derivative with respect to x. Pni j minus 1 minus 2 pij pi ij minus 1. And minus rho, we're going to use center difference for these partials of the velocity that appear here. So let's write u. I'm gonna skip the n's here, just to write a little bit. Un little less u I plus 1 comma j minus u I minus 1 comma j divided by 2 delta x, and this one appears twice, so it's a squared, plus 2 times we have the partial of u with respect to y, so u I j plus 1 minus u I j minus 1 divided by delta y, and dv dx. So that one is v I plus 1 comma j minus v I minus 1 comma j divided by 2 delta x. And we have still this other term here that has dv dy, and it's squared, so v I j plus 1 minus v I j minus 1 divided by 2 delta y squared. Here's where I have a sign that I have a problem with. Let me just write it like I have it, and I will have to confirm why I have this sign like this, because I don't understand. We have 1 over delta t, and we have, it was du dx plus dv dy, correct? So du dx, u I j plus, no, du dx, so it's I plus 1 comma j minus u I minus 1 comma j, and divided by 2 delta x, and plus v dv dx, so vi j plus 1 minus vi j minus 1 divided by 2 delta y. And I think I've got everything there. And I'm exhausted. Okay, so we've got everything written out, and now I think I need to give you the, I'm not going to write the transpose form. You know you can transpose by isolating un plus 1 ij, vn plus 1 ij, and p n ij. I'm not going to write it out. I think you've seen it enough, and you can do it on your own. And what we're going to use for initial condition here is going to be u, v, and p equal to 0 everywhere. And for boundary conditions, we're going to use u equal to 1 at y equal to 2, u and v equal to 0, x equals 0 to 2, and y equals 0, only because at y equals 2 we're going to apply this one, u equals 1. So we've got, that's basically y equals to 2, this is going to be a box, right? And y equal to 2 is this line. So in this line we have u equal to 1. Here we have u equal 1, and we have u equals 0 everywhere else. in every other 0 and 0. Basically a no-slip boundary condition everywhere. This is supposed to be cavity flow, so you have no-slip boundary conditions everywhere except here. And what else? We have some boundary conditions on the pressure. We need some on the pressure. We're going to have P equals 0 at y equal to 2. Basically that indicates that this is at atmospheric pressure. And we have dp dx equals 0 at y equals 0. And finally, dp dy equals 0 at x equals 0 and 2. Okay, so now notice that we're going to use this iterative method for the pressure, and we're also going to loop over time for the velocity, and basically our outer loop is the time loop. So that's why I've drawn this line that will continue on the next line, because now my pseudocode doesn't fit in one page. We need 2 pages, because basically remember the code that you had for the Poisson equation and the code that you had for the 2D burgers, all of these are going to work together now. So we have a couple of pages of code. So you see here I've initialized everything, 0, u, v, and p. I've created my grid of x and y values according to a certain number of steps in x and y. The nt is the number of time steps, while I also have the artificial time variable, which is the number of iterations for the pressure. So we have the actual time and the artificial time for the iterative method that we've just discussed. This double loop here, go back, is basically only filling up the values of b, the right-hand side of the Poisson equation, which for step number 10 was simply 2 spikes. For step number 11, you're going to have this big chunk of things that are on the right-hand side of the Poisson equation for pressure. So you have to write all of this, and you can store it in some sort of variable, auxiliary variable b for your source for the Poisson equation. And that is all that this double loop is doing, filling up those values. Then here we have our iteration on artificial time. This guy over here is the iteration on artificial time for the pressure. So now we have the same thing that we had for pressure, and you will have had that. You will have done that for step number, well, both 9 and 10. But this b is different now, but you've just calculated and shown you that you calculated before. But basically, this code doesn't change. Okay. Then you have your Navier-Stokes equation here, filling up the values of u and v. And one time step then is the whole thing, right? Calculating the source term, the right-hand side of the Poisson equation, iterating on the Poisson equation, then filling up all your values of u and v. Then, at time step number 2, you do that all over again. Is that clear? In terms of the flow of the code in your head, what it needs to do? And this, of course, here's the code that does all of this. This one actually has the viscosity here because that's the Navier-Stokes equation, but like I told you, I'm leaving out the correction terms. They're just correction terms for the pressure so that we ensure that continuity is satisfied. So that is step number 11. Step number 12 is basically exactly the same as before, is exactly the same equations as 11. So we don't need to write them again because it's the same equations, but add a source term f to the equation for u. The first equation, Navier-Stokes equation. This f is simply going to be equal to 1. Nothing strange. And we're going to have different initial conditions and boundary conditions. Initial condition is u, v, and p equal to 0 everywhere. The boundary conditions are u, v, p periodic. So now you get to use your periodic boundary conditions from the previous steps at x equals to 0 and 2, u, v equal to 0 at y equals 0 and 2, and dp dx equal to 0 at y equal 0 and 2. So basically now you have a box like the previous one between 0 and 2, but you're going to have u and v equals 0 here, u and v equals 0 here, so it's no-slip boundary conditions on the top and bottom, and you have dp dx equals 0 at those two places, and this is periodic, so whatever happens out 2 and 0 in 2 happens at 0 here in x. And in addition, you have the source term in u, which is going to be this additional imposed flow, which is going to produce basically channel flow. It's like, and you're going to see, of course, the effect of the no-slip boundary conditions here, slowing down your velocity close to those two walls. This is what you should see. Clear? Do I have Sudoku? No, I forgot to add the Sudoku for that, but it's same equations. So all you have to do is add 1 and change the boundary conditions.